Thank you. I was really fascinated to see this history, lesson in history, where I think we all have a lot to learn. I'm afraid my own history, we only go back to 1967, which for us as a community also is already pretty prehistoric. But I think it's excellent to really say, well, we have roots that go much, much further back than that. Okay, so in this talk, there's going to be some history. I'm going to give you my personal recollection how and why I think objects became mainstream, which is, of course, our environment for a long time now already, and why I think that functional programming is about to become mainstream now. And then I want to explore the question whether we can have to choose between object-oriented programming and functional programming, or whether we can have the two and what form this could take. So my personal involvement goes back also pretty prehistoric. I was actually working first on, my first thing that I did is I write a Pascal compiler on an Osborne 1 computer that was an 8-bit CPM Z80 computer in the early 80s, and then I became a PhD student of Niklaus Wirth in Zurich. I worked on Modular 2 and Oberon. That was a transition from procedural to object-oriented. Oberon was an object-oriented language, Modular 2 no. Then I actually fell in love with functional programming. I did a lot of research. I worked a little bit on early Haskell, on lambda calculus. And in 1995, I met my former boss at IBM, and he told me, look, you programming language persons, you should get out of your field. The language war is over, C++ has won, there's nothing left to do for you. Of course, 1995 was the year Java came out. So I got involved with Java very, very early on. I wrote a series of compilers that became, one of them became the JBuilder compiler of Poland, and then a later one became the javac compiler of Sun, which is the compiler that I think most people here are using still. And the way I wrote javac was that essentially we started writing extensions of Java. The first one was called Pizza. The second one was called GJ, that was a shorthand for generic Java, and that led to Java generics, and that also led Sun to essentially take over the GJ compiler as their standard javac compiler. Only for 5 years they actually disabled generics until they were finally deciding to put them in the language. We had delivered the thing to them by 1999, and I think they came out in 2004 or something like that. Myself, from about 2000, I was working on new things, so instead of making Java better, my ambition was to make a better Java, and that eventually led to Scala, which is where the aim of Scala is really to find a fusion, a unification of functional programming and object-oriented programming. Why the title of the talk? Well, I thought it was topical because there was a fairly influential paper that was written here in Paris at ENS by Giuseppe Castagna, which was called Covariance and Contravariance, Conflict Without a Cause, in 1994. At the time, the controversy was about Eiffel's somewhat non-standard interpretation of type theory. So type theorist says, no, it has to be non-variant or contravariant, and Eiffel said, no, it has to be covariant. And Giuseppe tried to find a synthesis between the two. So I'm going to try the same in the context of objects and functions a little bit. So how did object-oriented programming get started? Little history quiz. What was the first popular object-oriented language? There was one even before that, Simula, which Strauss said influenced him greatly to write C++. He wanted essentially to get Simula on top of C. So Simula was the first object-oriented language, came out in '67 and was for simulations. But it actually was a general-purpose language, a very nice one, actually better than, in my opinion, better than any of the other languages at the time, like at the time you had COBOL, ALGOL, PL1, languages like that. The second popular object-oriented language is, like you've said, Smalltalk. So that came out end of the 70s. There was a famous Byte article that was devoted to Smalltalk. The whole issue was devoted to Smalltalk. And I can remember very well that I was reading this and I was totally confused. I was saying, well, this looks fascinating and intriguing, but everything's so different. And I couldn't make a lot of sense of it. So obviously, even though though object-oriented programming for us is second nature, there was a time where people were just as confused and bewildered as a lot of people are with functional programming today. So why did object-oriented programming become popular at the time? Was it maybe because of encapsulation? No. Code reuse? Don't think so. Dynamic binding? Well, maybe indirectly, I'm going to get to that. Dependency inversion? Liskov substitution principle? Open-close principle? No, you've got to be kidding. It's because of the things you could do with object-oriented programming. There were certain things you could do with OOP that you couldn't do with the previous approach of procedural programming. What was that? Well, it actually pays to go back and say, well, what were the first two successful languages? Simula and Smalltalk. Simula was for simulations, Smalltalk was for GUI widgets. What do they have in common? Or rather, what's different? What was different before? So the traditional approach, the traditional data structure that people had for all times was something like a linked list. And you had two cases, a linked list is either empty or non-empty, and on the other hand there were an unbounded of operations you could do with linked lists. You could map them, you could reverse them, you could print them, you could get a certain element, you could insert an element, you could delete an element, and so on. The number of operations was literally unbounded, but the structure of a list was very, very well known, empty or non-empty. With simulation, that was suddenly different. People encountered something which didn't fit into that mold. Because with simulation, you actually had a fairly modest number of operations, essentially bring yourself up to the next step, display yourself in some way, or form an aggregate of some kind of another. But you had an unbounded number of implementations of the things you wanted to simulate. That could be a car, or a road, or a molecule, or a cell, or a person, or a building, or a city. It didn't matter. They all had the same operations, but you didn't know how they would actually execute these operations. And for GUI widgets, it's actually exactly the same situation. Again, you have a fixed number of operations, things like redraw, get bounding rectangle, move, but you have an unbounded number of implementations. A GUI widget could be a window, a menu, a letter in some font, a shape, a curve, an image, a video. Again, it's unbounded. And in both of these cases, you need to execute a fixed API, a fixed number of operations with an unknown implementation. Now, it's possible to do this in a procedural language such as C. What you would do is essentially you would use a pointer to a function object and execute them, but it was just too cumbersome. People didn't want to do that. In fact, I remember there were attempts to do that. The so-called presentation manager, that was the window manager of OS2, IBM's failed attempt to actually go up against Windows, that didn't use an object-oriented language. And people hated it. They said, well, this is actually no fun to program things that way. So they were forced into object orientation because they wanted to write cool GUI widgets. That was the truth. And then, of course, the other things came later. I'm not at all denying that object-oriented programming has a lot of modeling advantages. But to get people over the hump and say, do it and then you will find out the other advantages, it takes something else. So what does it do with functional programming? So I believe just like OOP did then, functional programming has lots of methodological advantages. What people that know both fields cite is you make way fewer errors, you have better modularity, higher level abstractions lead to shorter code, and overall increased developer productivity, just to name some of them. But I believe also these advantages alone, they're not enough for mainstream adoption. After all, you could say functional programming in one form or another has been around for 50 years, so why didn't it become popular before? So I think the answer is, well, it needs a catalyzer, something that sparks the initial adoption until the other advantages become clear to everyone. So what could this catalyzer be? Because I think we do see a resurgence of functional programming by all sorts of measures. For instance, I see the scientific conferences where object-oriented programming was way more popular than functional programming 10 years ago, and now it's actually the reverse. So ECOOP was 3 times the size of ICFP, the functional programming conference. Now ICFP is twice the size of ECOOP. So you see the shift in trend. But why now? So I believe that is actually due to forces that are coming in essence from hardware that drives off the complexity, namely multi-core, which essentially forces us to become parallel, and cloud computing, which forces us to write programs that are good at concurrency and distributed programming. And current languages and frameworks that just have a lot of trouble keeping up with that new paradigm, because we've all seen that locks and threads, they just don't scale. You can't write, or it's extremely hard to write a complicated, scalable application using locks and threads. They become very, very brittle, very error-prone, and you still might have a lot of bottlenecks in them. So you need better tools for ordinary programmers, for the masses, that give you the right level of abstraction to be able to program these machines and data centers. So here we see a triple challenge where what we need to do now in the future is no longer plain old sequential programming, but we need to become parallel in order to make use of multi-cores and GPUs, clusters. We need to become reactive because we have to deal with asynchronous events that might come from some other computer in the cloud, some service, some user interaction, and we need to become distributed, so we need to learn how to deal with delays and failures. And it turns out that mutable state, which was our daily bread until now, is actually a liability, a big liability for each one of these. Once you distribute your thing, you get a huge problem with cache coherence. You want to cache things, but then if your caches disagree on different computers, you have a consistency problem. If your data is immutable, you can cache all you like and you will never have a problem because your data won't change. So mutability, cache coherence, big problem. Races, versioning, all of these things are similar. So the root of the problem, that we see here is that in this new world with concurrent executions, if you mix that with shared mutable state, then the result will always be non-determinism, because you have essentially different execution threads at different speeds, and they might access your state in different ways on different compiler runs. And that's actually fundamentally true no matter what your abstractions are. It's true for threads and locks, but even if you upgrade to shared state with transactions, fundamentally you have the same problem. So in a nutshell, you see this here in the small window here on the right, where you have a simple variable x, and you have two computations, and one adds 1 to x, and the other multiplies x by 2. And that can give you 0 or 1 or 2 depending how these things are executed. If you say async is atomic, so it will be executed in block, then you still, you avoid the null case, so x can no longer be 0, but you can still have the problem that it could be 1 or 2 depending on which order you execute these two blocks. So non-determinism then is a fundamental consequence of parallel processing in mutable state. And non-determinism is what keeps programmers awake at night, and not only for productive work, but also for nightmares and things like that, when they say, well, I have one execution thread and it doesn't work, I have a bug, I put in some instrumentation code, the bug goes away. Why? Because the timing of my processes changed, the race went away, or the race ended in a different way. So what do you do with fun stuff like that? So to get back to sanity, so to largely deterministic processing, it means that we have to reduce, ideally avoid, but I won't go that far, just reduce, be very, very careful with mutable state, because that's the thing that will actually cause us the problems. And avoiding mutable state means programming functionally. So I think that's really the catalyzer. Another way to look at that is that if you have already some experience with function programming, then you will probably have noticed that your way of approaching a problem is completely different from imperative programming. As imperative programmers, we're very much trained to think in terms of time units. I have to initialize this variable before I can use it. I have to grab this lock before I can enter the critical regions. First I multiply this variable by 2, then I add 1 to it, and I can't really mutate these two operations. So time is very essential here. Whereas if you think functionally, then that doesn't really matter. The time steps that you need to construct an eventual results are completely insignificant. Any sequence of sub-operations will give you the same result, as long as your computation is purely functional. So if you add parallelism to that, then in terms of space, you don't have a problem. You just say now different parts of my subcomputations will be executed by different computing processes in parallel, and the end result will still be the same. But if you think in terms of time, then you have a problem that now you don't have a single timeline, which is quite manageable, single sequential, but you have multiple ones, and they might cross each other. So each cross here is a data race where one might get first to the point or the other. And the more crosses you have, the more you tie yourself into knots. So what you then need to do is you need to essentially separate these threads that they don't knot into each other, and that means I have to put in some locks and atomics and things like that. And I have to put in enough so that all these locks are avoided, but not too much so that my application becomes too sequential, too blocking. Just the right amount, and it's very hard to find this right amount, in particular because we have to, as programmers then, to think of all the bad things that could happen, all the possible races, and that's something that is, I think, deeply not in our nature. We're sort of optimistic animals. We want to achieve something, we want to say, well, I want to put things in place that I get there. I don't want to think about, well, what are all the possible weird situations that could happen and that could destroy what my result should be, and how do I prevent against them. That's just not fun, and I don't think we're very good at it. So the essence of functional programming then is that instead of stepwise modifications of mutable state, which is what we did so far, we concentrate on transformations of immutable values. And these transformations are often bulk transformations. So in a single step, I could map a structure to some other structure. So let's see an example. So here's a class in Java. Let's define some classes first. So it's a class of developers, and we all can read that. A developer here has a name and a list of commits. And we have the typical constructor thing. I will show you the code in this session, both in Java and in Scala. So in Scala it's quite a bit shorter. So the class developer, you just say it has two parameters, a name and a sequence of commits. And those two parameters, they are also fields of the class. That's signified by these two vowels here. And furthermore, the fields are immutable. You can't change them later. If they were mutable, let's say you wanted to model a developer with a time-changing sequence of commits, then you would just write a var here instead of a val. So Scala is not opinionated that it says you must write functional, but it sort of encourages it. It's the recommended default, but if you need to drop back to imperative programming, then that it's just a single letter away, var instead of val. Okay, so that was the class. So let's look at a usage of this class. So what does that program here do? Well, it's pretty typical collection code, right? So we have a list of devs, and we set things up, and then we have a loop for going through all the devs, going through all the commits of the devs. If the length is greater than the previous maximum, then update the maximum and set the longest commit, and then finally we add the developer def and the longest commit to this longest commits. Aha. So what this seems to do is, for each developer we get a pair with the developer and its longest, the size of the longest commit of that developer. Right. It's a bit of a slog, but I guess most people here are perfectly used to this sort of code. But remember that this is the idea here. We do stepwise modifications of mutable data structures. So in particular, this list longest commits here, it gets built up incrementally by adding to it one after the other. Okay, so I'm going to shrink the Java example a little bit. In Scala, the way I could write it in exactly the same way as in Java, but people usually don't. So what people usually write is something like that. So you start with a sequence of developer devs, and then you say, well, I want to map a function for each developer, and here's the function. So it's a def is the parameter, and it returns a pair of the developer itself and the taking the commits of the developer and the maximum according to a function. The function is for each commit I give the length. So that means I take the maximum commit according to this comparison function which says compare the length of the two. So what you see here is that example does the same thing using not a loop but some predefined operations that act on the whole collection. They don't even act on the collection, they take the collection, they don't mutate it, they generate new collections from old collections. That's these transformers. There's a slightly more familiar way to write this thing. So here you have a slightly modified Scala program which uses something that looks like a loop. You say for developer taken from developers yield, and then comes the pair, developer and developer commits max by length. And that looks like a loop to you, but in fact it isn't, because it turns out that this for expression maps into exactly the code that I've shown you in the previous slide. So these for expressions, they give you familiar loop syntax, but that's not what they are. They map into these transforming, purely functional transforming operations. Why is this important? Well, we said the new challenge is parallelism and concurrency. So going parallel, challenge write the Java example in parallel, that's not so easy, and I don't have time in the keynote to do it, and I don't have space on this slide to give you a solution. In Scala, all you need to do is this. So you add .par to defs. So we say for developer taken from defs in parallel yield the other thing. So what this does underneath is it takes the developer's collection and it turns it into a parallel collection. And parallel collections, they have the same operations as normal collections, but where possible they are executed in parallel. In particular, we have seen that this for loop maps to a map operation, apply a function to each element, and that map will be executed in parallel. So you could say, well, great, challenge solved. So why did I say parallelism is hard? This is trivial, this is easy, right? So, well, there's actually a catch. So what's the catch with that? Well, the catch is, by writing .par, you give to the system the complete authority to rearrange the program in any way it likes. So it will probably, for maximum performance, execute some of these things sequentially in chunks and parallelize them the chunks. You have no more control over the order of your operations. So if the function that you execute in a par contains side effects, chaos will break loose. You don't really know when these side effects will happen. So you will have side effects that can happen at unpredictable times. So the price for this simplicity, that you can write parallel code very easily in this thing, is that you have to become functional, because any side effect here will actually be a huge liability for the correctness of your system. So that's the price that you have to pay here. Okay, so that was parallel. I'm going to do one other example, and that's about reactive programming. So here you have a typical scenario, an online store where you can have orders, make payments, search for products, and so on. And here you have a typical operation where you say, okay, I want to get the user by its ID, I want to get the orders for a given user, given its email, I want to get the products for each order, and I want to find out what's in stock for these products. So one step after another. And all of these things are very easy to write, as you can see. And they're easy to write in Java, and in Scala it wouldn't be much different. So here's the equivalent Scala program with the same operations and just a slightly different syntax, which again emphasizes that these quantities here should all be immutable. But now the question is, okay, if I do that and one of these auxiliary services here, the payments or the search or whatever, is non-functional, is offline or very slow, then that will slow down my whole online store. My threads will sit there and go bang bang to the search service and won't get anything, and I will hog my threads, and my throughput will go down and my server will become non-functional. So I don't want to do that. So what I want to do instead is be reactive or asynchronous. That means that if I send a request to the payment service, I don't want to hog the thread. I want to say, well, when you come back, then here's how to continue. But I don't really want to block any threads while I do that. And that's also possible. So here you see some Java program that actually uses now the Scala API for that, because Scala has very powerful futures-based API that let you write this reactive programming thing. But you will agree it's not exactly pretty. So that means that most programmers in Java wouldn't write code like that. It would wouldn't feel right. It would feel boilerplatey, indirect. So as a result, it's actually very hard to get good asynchronous stable performance out of this, out of an online store where you have to be asynchronous. So in Scala, what you would do instead is you would use a for expression. So by putting these things in a for expression, and they would be slightly reinterpreted that now each of these things doesn't give you a blocking result, but a future. So that means it will give you at some point in the future the result that you're looking for, and at this point you will continue the computation. So this looks like a loop, but it actually isn't. It's a far thing from a loop. So what this thing will do here is when it goes to, let's say, get orders for user, it will compute a closure, a lambda, that represents the rest of the computation, and when the orders come back, that computation will be executed. So in the example before, that was essentially done explicitly. Here I was constructing all these computations. But here with the for expressions, it's implicitly. Now you might say, wow, this is a really powerful language for online stores and async computing, but the take-home point here is the translation of for expressions to methods like map, flat map, filter, is completely universal. It works for all possible interpretations. So nothing in the for expression gives you either a loop or an asynchronous computation. It's much more general than that. It just maps into a set of 3 standard functions that you can define in your libraries to do the things you need. And that way you can very, very successfully hide the complexity in the API, in the library tier, and user applications can concentrate on the domain and be much, much clearer. They're not polluted by the accidental complexity to actually deal with either the incremental modifications or the async computations and so on. Okay, you could say, well, if you do that, then these futures, they're still sequential one after another. If I want to be better than that, can I actually do these requests in parallel? So ask several web services in parallel and get back the result. That's only a tiny refactoring away here. So here you would see we have 2 requests, get orders for users and get profile user, and I just put them in a pair that gives me 2 futures that essentially execute in parallel, and then I collect the things with orders and profile. So that means that I don't need to have these things sequential anymore. I can ship them out in parallel if I want to. So now I've told you the wonders of functional programming, so you might be tempted to say, but what about objects? Should we just get rid of our whole history as far as we can think? Is that like legacy stuff? Actually, I don't think so. I think that objects are really orthogonal to what else we do. I believe objects can be combined with imperative and have been combined, of course. They can be equally well and equally profitably be combined with functional. Because objects, after all, they're all about modularization. The central question that objects answer is, what goes where? They give you containers in which you can put stuff, data and operations and things like that. And very elaborate ones, so containers that with dynamic binding actually hide the actual implementation, that can inherit from each other, and so on. And in the end, I think that question is very, very important. I mean, for instance, the largest code base in Scala that I know is now over 1 million lines. I can't imagine how you would deal with a code base like that without this very strong degree of modularization. You can't just put things in a global namespace and just hope that everything will work out. So I think that actually that's some of the problem with a lot of functional programming languages, that they don't deal with this issue at all. So if you look at a language like Haskell, then Haskell doesn't really have a module system. And that means it can scale up to a certain amount, but I believe scaling further is very, very hard. Scaling to systems where programmers don't even know that this component exists in the system, and in a million-line system, that's the definition of a million-line system, is very, very hard. You might say, well, don't write these systems, but, and I might agree with you, but it's a fact that some of the applications, they do grow like that. Okay, so the question is, I believe objects are great for modularizations, functions are great for writing your program logic. Can they both be combined? And sometimes it actually feels very hard it feels very much like sitting between two chairs, which has largely to do with the fact that the two communities really often don't understand each other and sometimes really have very low opinions of each other. So for some object-oriented programmers, function programmers, there's these mad scientists that cook up these things totally incomprehensible, and maybe they will destroy the world. And for some function programmers, object-oriented programmers, they're these guys in suits who push out business applications and are evil managers otherwise. That's a pity. I would much rather like things to be like this. Sit on the beach. But to get there, we need to get rid of some baggage first. So what baggage do we need to get rid of? Previously, the definition of objects was, objects are characterized by state, identity, and behavior. Grady Booch. And that was the state so far, and I think that phrase has probably held back the state of object-oriented programming for at least a dozen years. Because it actually turns out that all the objects that I've shown you here in this talk, did any of these objects have mutable state? No. Does Java string have mutable state? No. Is Java string an object? Well, I would say very much so. It has methods. This idea of objects need mutable state or they're not first-class objects is just totally wrong. And I was actually quite shocked that I was at a very interesting seminars with leaders of other programming languages, including some very popular object-oriented programming languages, and they assured me, no, that's the case. Objects need state. Without states, you don't have objects. So it's very much even in the opinion today. It's not something of the past. So I believe we should eliminate or reduce the mutable state, and it works perfectly well. You can still have objects that way. Identity, that's another one of these things. So who here has not fallen in the trap that you write string 1 equals string 2 and then it didn't do what you wanted to? Yeah, right? So that's another thing. So why does equals have to be pointer identity of two strings? What matters about a string? What's in it? Not what address in memory it has, right? So that's another thing. That's this dogma, object have an identity and your main operations must test for this identity. That held us back. So you want structural or user-defined equality, and you want to make what Java programmers write as the equals method be the same as when you write equals as an operator. And finally, of course, the behavior part, while that's true, objects essentially are containers for functionality, and we should concentrate on that one. So Scala then is essentially the language that tries to follow that in its purest form. So it's really this fusion of object-oriented and functional. It refuses to put on any of the traditional functional things like algebraic data types or things like that, and models them all with objects. And at the same time it imports the fundamental abilities of functional programming into object-oriented programming. So it's a unifier in that sense. It actually turned out, which was not intended, but as a side effect, that it turned out to be a unifier also in another dimension, and that's that Scala is both a fairly popular scripting language. It actually won the Java 1 Script Bowl last year, which is sort of a popularity contest for scripting languages, and it's at the same time it's very safe and performant language, which is really the backbone structure of an increasing number of companies. Well-known names, of course, are Twitter or Foursquare or LinkedIn and companies like that, all banked really on Scala, and not just for like margin things, but really that's the core part. So for Twitter, for instance, the search is written in the search functions are written in Java. The core part, the whole message delivery infrastructure, is written in Scala. So to find out more about that, I think I'm at the end of my time. There's a BOF tonight at 8 o'clock. I think it's here in the auditorium for the Scala user group. Tomorrow, the last talk at the conference by Guillaume Bort and Sadek Drobi is about web-oriented architecture in 50 minutes. And that essentially tells you in 50 minutes live coding what I tried to tell you with this little future example. So how do you write async applications that scale? And if you want to really find out more, then there's a class on functional programming principles in Scala on Coursera. The second iteration just started this week, so if you enroll this week, then you won't have missed anything. It will go for 7 weeks, and the workload is maybe 5 hours a week. So far, we had 80,000 inscriptions for this course. Another thing, if you're really into Scala, there's Scala Days coming on June 10th to 12th in New York, which is the meetup of the Scala community. We've over 40 speakers secured, and Rod Johnson of Spring fame will give the keynote. Thank you.